Okay, again, I'm going to make a small summary. I think it's very important that you understand how the whole course works. The first part was introduction, graph theory, game theory. Now we have applications, and it's first on game theory, concentrating, and then there will be stuff on graph theory. Remember we saw options? Options, second price, very important. And then markets, which is generalizing auctions, and different kinds of markets. So the matching market is classic buyer-seller, supply to command. Price is coordinated. Then you add traders on supermarkets that introduces monopoly competition. And now we're going to do nodes negotiating, bargaining with each other. So this one is actually pretty neat. I will show you how it works. So today we're going to do how nodes actually negotiate with each other on the network. Okay? So negotiation is when I'm talking to someone else and back and forth, and we kind of agree. I want to buy the house for $150,000, and the person wants to sell for $200,000, and we negotiate, and sometimes we agree. So that's negotiation. Nodes negotiate with their neighbors. So I negotiate with people I know, not with everybody, only people I know. Depends on the position of the nodes. You in psychology also. So this is very interesting. It's a combination of graph theory and game theory, graph theory and psychology. And we're going to introduce this. How do nodes negotiate? Experimental results, and then a theory called the theory of balanced outcomes. This is the best explanation we have of how it really works. And it's based on three ideas: Nash bargaining solution, alternative games, stable outcomes. So this depends on the node position in the network. Remember, it was always important. Remember bridges, long time ago? Well, the bridges, the nodes that are on the bridge are very important. They have a lot of power. Remember, traders can have monopolies, or the trader maybe is in a perfect competition and has zero profit. So it all depends on the network. Okay. So I'm going to show you a bunch of examples. So today it's going to be mostly intuition, and you can imagine what the theory has to be. So here's two people, A and B. And they negotiate. A wants to buy a house, B wants to sell a house, and they're talking to each other, and they have all kinds of reasons. Maybe B is in a hurry, maybe A is not in a hurry. That gives A more power. Okay. So power is a relationship. Power is not a property of a person, but it's property of this relationship. A and B are doing something. We call it negotiate. And both of them get something out of it. Payoff, revenue, friendship, whatever. And maybe one person gets more than the other. How is it possible? Maybe one person is more talented, so they get more power. Magnus Carlsen is playing chess against Donald Trump. I think I know who's going to win, okay? And I know one person is more talented than the other, and it's not a stable genius, okay? It also depends on the position in the network. Position in the network. Okay, now let's give another example. Here's a network with 5 people, A, B, C, D, E. B knows A, C, and D, but A and C only know B. And D knows B and E only knows D. So somehow, B seems to be very powerful here, because B has a lot of influence. Okay, there's actually several reasons. How come B is more powerful? Maybe B is powerful because A and C, they only know B. So they are dependent on B. That means B has power over them. Or maybe it's exclusion. B can exclude can say no to A and C, and they cannot talk to anyone else. Or maybe satiation. Maybe B has so much source of income that B is so much stuff is flowing into B that B can afford to be very picky. Okay? B can place higher demands. Or between this, if C wants to talk to D, the only way is through B. So there's many ways that B can get power. Okay? So we're going to study this in the real world, how human beings work when they're in this kind of situation. Okay? So it's not obvious. We're going to make a simple model. So I will define the model and then we'll make examples. This is called network exchange model. Okay? So basically, the idea is we have a graph, a small graph, for example, back here, A, B, C. That's a big one here. We will put a fixed amount of money, $1. Let's talk about dollars. $1 on each edge. And here, A and B will negotiate and divide up the dollar. Okay? Or B and C negotiate to divide up the dollar. But you can only do one exchange. If B divides up the dollar with A, then C gets nothing, 0. Okay? So you put a fixed amount of money on the edge that can be divided between the two endpoints. Why is it always changing? Okay? Is it a problem with the... Is it set to advance? That's not good. So each node can exchange one neighbor, B with A or B with C, but not both. Okay, this is called one exchange rule. This is our model. We make a model. If B buys the house from A, then B will not buy the house from C. Okay? And the node will be negotiating. So this is like they're always talking. B and A are somehow discussing, and they agree on how to split the dollar. Okay? This free-form negotiation. The fixed time limit. So this is something humans, we can experiment with humans. Okay? And multiple rounds. And eventually maybe there's somehow something converges. In each round, new money is put on the edges. And then again, the money is divided. And you do it again. And eventually you can see where the power is. Okay? So this is kind of like an experimental thing. So here's an example. A, B, C, D, E. Each edge starts with $1. So that's in green, $1. And then now we do a round. In this round, you can see that A has agreed with B. And they split the dollar. A gets 30 cents and B gets 70 cents. And B has agreed with E. B gets 80 cents and E gets 20 cents. And C gets nothing. Because B and A have negotiated and D and E. So in this example, both A, B, D, E get some money, but C gets nothing. Poor guy here, huh? Nothing. So only 2 of these values are exchanged, the other 2 are lost. Okay? So this is something, this is our model. This is something that people try to do with real human beings and see what you get. And then you try to explain a theory, how it works. So this is kind of a theory of how people negotiate and how power comes from the network. Okay? So you see how it works, huh? You make some of the lines become red when there's an exchange, and the ones that are not exchanging get 0. Okay? So some of these dollars are lost, and the ones on the red lines are exchanged. Okay? See how it works? Now, real humans were done, experiments were done on human subjects, okay? So this actually gives interesting results, and we're going to explain some of these results. It's very intuitive, and actually it's robust. It means if you do these experiments, psychologists have done these experiments, you get kind of always the same result. There's some real power in the network, okay? So this is very interesting, and we will use this result to determine outcome of negotiations. So the theory of stable outcomes, and the main theory is called the theory of balanced outcomes, okay? So I'm going to show some examples now. So before we make a theory, we're going to show some examples, and then we'll see how you can make a theory out of this, okay? So here's the simplest example. A and B. Two people are splitting money. Two people are given a fixed amount of time in which to agree how to split $1. So if you put two people next to each other on a table, and you let them talk until they agree, what are they going to agree on? Well, it's completely symmetric. You might say they would split half and half, 50 cents, 50 cents. And when you do real experiments, you get 50-50 split, okay? So this is very intuitive, right? This is how you expect things to happen. So, but this is the simplest one. What about more complicated networks? Things change a lot. Here's a 3-node network. 3-node, A, B, and C. So somehow you can imagine that B has more power, because B can be talking with A, and B can be talking with C. And B can tell A, you have to agree on less, because if you don't, I will drop you and I will do with C. B has alternative, huh? So A kind of says, ooh, B can always go to C, so maybe I agree on less, just so that B goes with me, okay? So as B negotiates with A, it has power to go to C, and also for C. So you can see that A and C are weaker. At least one is excluded from each round. Only one of these is going to get money. Okay? If you're excluded, then you get 0. So A doesn't want to be excluded, so A is going to agree to get some less amount, which is better than 0. So what happens when you do this real experiment in real life? You get this result. It's very funny, huh? B will usually, on average, receive 83 cents, and A will receive 17 cents. That's kind of weird, isn't it? This is how human psychology will fix it, do it. And B will get a lot, but not 1. So A is agreeing to get a little bit, but for A, it's not. A will not agree to get less than 17 cents. So A has some willpower or some power to get 17 cents. But this is with one exchange rule. The other one is excluded. So here C would get 0. If you allow 2 exchanges, one and the other, then it's actually more equal. If you say every time there's 2 exchanges, that means both A and C get stuff, then A and C have more power. And together, they're like as powerful as B somehow, huh? Together. So actually, each will get 1/4, and that's how what you see. And B gets 50 cents. So B is still more powerful, but not as much as the one exchange rule. Because here, both A and C are getting something. So that means the threat of getting 0 is not there. So they get more. Okay. So B has a lot less power. But B still has more power than A or C. Yeah? But B has the same amount of power as A plus C. See, that's interesting, huh? So how you do the exchange is also important. But in the one exchange rule, B has a lot more power, but not infinite. A will still get something, okay? 17 cents. Okay. So you see this gets more interesting, huh? And now it gets even more interesting. Here, let's look at this one. The 4-node path. This one is actually pretty subtle. Now there's two possibilities. Either A, B, and C, D, or BC. Okay? So either A and B exchange and C and D, or B and C. So B and C are always getting money, so they're more powerful. But A and D are weaker. Okay? B has some power over A, but it's not as much as in the 3-node case. Okay? If B, the reason is because C has an alternative. In the previous case, B can exclude A and go to C. This gives B a lot of power. Here also, B can exclude A and go to C. But the C is more powerful here because C has an alternative. C can say B, no, I want more because if I don't like you, I can go with D. So B is not as strong here as in the 3-node case, you see? It's because C has an alternative. C could make a deal with D. Okay? So B can still threaten to exclude A, but it's not as strong because C is stronger now because it has an alternative. Okay? So if you actually do it, there's some fluctuation. B is still more powerful than A, but A gets 37 cents. B gets 62 cents. Actually, there's some fluctuations. It's not completely fixed. B gets from 58 to 67 cents. So on average, it's like 5/8, and A is like 3/8. So A has a lot more power here than in the previous case. It's because of the 4th node. So that 4th node, which is sitting behind C, gives A a lot more power. You see, it's subtle, huh? It's interesting, huh? And this is real experiments, huh? If you put 4 people on a table and you allow each of them to look at its neighbors and discuss, then that's what you get. Okay? This is the psychologists. So our theory is kind of looking at psychology now. So real negotiation kind of works like this, huh? So C and D, and A and B, they could be real people trading, exchanging something. So here's another one, the 5-node path. So now we have 5 nodes. C is in the middle, but C is not strong here. C is not strong. C can talk to B or D. So you might think C has a lot of possibilities. It can talk to both B and D. But each of B and D has an alternative. B can talk to A, and D can make a deal with E. So both B and D could exclude C. So C can still get 0 here, right? But still, if you do the experiment with 5 people, you see C has actually more power than A and E, but the most powerful ones here are B and D. Okay? If you do the 2 exchange, then it has more power, of course. Huh? If C can exchange with both B and D, then it will have more power because it won't be excluded so much. So this gives the line. When you have networks that are just little lines. So the 2-1, you can see how it goes. The 2-1 is half and half. The 3-1, the middle guy, is very powerful. The 4, the middle guys are also powerful, but a little bit less. And in the 5-node guy, the middle one is medium powered, and the most powerful ones are the ones right next to the edge. Okay, this gives kind of an idea of how the power goes in straight network. So how can we make a theory for this? It's kind of interesting, huh? So here's the network we started with. So what can we say here? So here, B has the ability to exclude both A and C. So B has the most power, A and C are weak. B and D have about equal power. D is also very powerful because D also can go with E. So D can say to B, give me lots of money, and if you don't, I go with E. And then B has to exchange with A or C, okay? So so B and D almost never exchange, and that means that E actually has also power. E's on the edge, but because B will almost never exchange with D, that means D has to go to E, and D and E will have similar power. Even though E is on the edge, somehow D is forced to talk to E. It's funny, huh? How it goes. And here's another one. This one has a name. It's called the stem graph. It's basically a triangle with one edge sticking out, which is like stem, 4 nodes, A, B, C, D. So these are forming a triangle. So what happens when you put people in this network? Well, usually what would happen is C and D will agree. They're kind of similar. And A and B will usually agree. But still, B is more powerful than A because there's a small chance that B will go with C or D. Okay? So B has a little bit more power than in the 4-node path. Okay? B is negotiating with nodes that are slightly weaker. So B has a little bit more power, but A has more power than before. So even though A is like on the edge, it will still have a fair amount of power because B is kind of forced to talk to A. That's curious, huh? So this is kind of all reasonable, huh? But now let me show you a network which is pathological, where there's no solution, really. The simple triangle, ABC, the triangle. This one, there's no convergent solution. There's no easy solution here. What happens? So what happens? Only one exchange can be done. So only one of these lines will become red, okay? If A and B agree, then C is left out. But let's say A and B agree to 50-50. Well, C will be talking to A, and C will say, if you come to me, I will give you 60 for 60 and not 50. So C can steal A from B. So it's unstable, okay? But now C and A are agreeing, and B also can butt in and say, I can give you a little bit more, come with me. So there's an infinite cycle. Whenever two nodes are agreeing, the third one can always offer more and steal the negotiation. So there's an infinite cycle here. There's no simple, stable solution. Okay? So this simple triangle, the only way it stops is to get a time limit. There's no stable solution here. It's funny, huh? In this one. But in the previous one, there was. In this one, there was a stable solution with the extra nodes sticking out. A, B, and C, D. Here, there's no stable solution because for every solution, the third node can always steal the negotiation by offering more. See that? Huh? Whatever AB or AC or BC agree, or they're agreeing on something, the other node, the one who's left out, should always offer a little bit more than one of them, or the one who's getting less. And that one will say, hey, I should go with the other one to get more. And it never ends. Okay? So this is all very weird, isn't it? Kind of weird, huh? So we want to make a theory about this. We're going to make a theory. So today I will only begin the theory, and then we'll see the rest next time. Actually, this thing is actually connected to what we saw before. Remember, we have different kinds of markets. The regular market, buy-seller, traders, and now bargaining. And there's connections, like auctions is connected to markets. So this is actually connected to bipartite matching markets. Sometimes. It's actually more general, but there is some connection. Like let's say we have a 4-node path, A, B, C, D. We arrange it like this. So B and D are sellers, and A and B are buyers. And A and B are negotiating. So B has one item to sell. That's like the edge, huh? And they're splitting the $1. Well, because B sells for X, and A buys for 1 minus X, so there's a payoff. Buys for X, so the payoff is 1 minus X, there the payoff is X. So it's like they're splitting $1, huh? The value of the thing is somehow split between the buyer and the seller. So this is exactly the same as they're agreeing on how to split $1. And since there's only one item, it's going up like that. And this one also has one item. Or maybe this guy sells the item down. So you can see that which of the buyers will buy. That determines the edge for the negotiation. So you see, the negotiation thing is like more general, because this is only working for the 4-node thing, for bipartite graphs. So splitting the money between two people is like buying and selling, in some sense. Okay, so this is all pretty weird, huh? You have sometimes convergence, sometimes you don't have convergence. So we want to make a theory. We want to explain this. So psychologists have been scratching their heads on this, and they tried to come up with a theory of this. Okay? So I showed you some examples, and we got some intuition, informal motivations. Let's try to make some kind of theory on this. And I make the theory in 3 steps. So we'll end up with a theory, which is called theory of balanced outcomes. And this lets you compute what the real negotiations between humans will give. And it actually seems to work pretty well, because this is explaining human behavior. Okay? And in order to explain this theory, I'm going to show 3 things. First, something called Nash bargaining solution, then ultimatum gain, and then stable outcomes. So these are like 3 principles, and when you combine them together, you can come up with a theory. Okay? So let me just show you one thing today, and then next time we'll show the real theory. So with this real theory, you can take any kind of a negotiation between humans, and you can predict how they will react. That's nice, huh? And it actually gives a pretty reasonable solution. Okay? So the first step is when 2 people are interacting. So now let's focus on 2 people. A, B. They're interacting. And let's focus on 2 people. And this is something called the Nash bargaining solution. So A and B are negotiating. We're how to split $1. So there's $1. How are they going to split the $1? Let's somehow extend this. This link is actually part of a bigger network. Okay? So the A is also connected to other things. The B is also connected to other things. But we don't show them. We only focus on AB. Okay? A can decide to go with B, or A can decide to do something else. Okay? And the same for B. You can decide to go with A or something else. So we will assume that A's outside option, A's other thing, gives it a payoff of X. And B's outside option gives it a payoff of Y. If that's true, how can they agree on AB? So if A is an outside option of X and B is an outside option of Y, then they might still agree to go with the A, go with B, and B with A. Okay? But only if they get more by doing that. Huh? A will only agree to go with B if it gets more than X. And B will only agree to go with A if it gets more than Y. So when does that happen? Okay? That can only happen if X plus Y is less than or equal to 1. If X plus Y is greater than 1, that means A will never decide to go with B, because A with B will only split $1. But if A and B do the outside option, they will get more than $1. Huh? X plus Y is greater than 1. So that means in order for A and B to work with each other, X plus Y has to be less than or maybe equal to 1. Okay? Otherwise, there's no way they're going to talk to each other. You see that? So this is a condition on these two outside options. So this will give us kind of an equation when we look at the whole network. Huh? We'll have a bunch of equations. So assuming X plus Y is less than or equal to 1, then A will ask for, of course, at least X. A wants to get more than X, and B wants to get more than 1. Of course, otherwise they're not going to talk together. They're not going to agree. So how do they do that? Well, there's actually a surplus. Huh? If X plus Y is less than 1, then if you do 1 minus X plus Y, 1 minus X minus Y, that's like the little bit of extra they get if they agree with each other. So they're actually splitting the surplus. You see, if X is 0.4 and Y is 0.3, that makes total of 0.7. And when they go together, they're splitting 1, which is more than 0.7. And 1 minus 0.7 is 0.3. That's the extra they get when they go with each other. Okay? So the negotiation is about splitting that extra. A will get a little bit more than 0.4. B will get a little bit more than 0.3. How much more? Well, they will split the surplus. So if I show you an example, if it's like this, if A has an outside possibility of 0.4, B has an outside of 0.3, together that gives 0.7. But if they go with each other, they will get $1, which is more than 0.7. But the difference is 0.3. This is the surplus. This is how much more they get if they go with each other. So how do they split this extra? Well, we assume they will split it 50-50. That's reasonable. Each one of them has already a guarantee. They will agree on splitting the surplus 50-50. So our prediction in the theory is they will split the surplus in half. So A will go from 0.4 to 0.4 plus 0.15, and B will go from 0.3 to 0.3 plus 0.15. So the 0.15 is half of 0.3. So 0.55 and 0.45. So the prediction if A, B have outside option of 0.4 and 0.3, the prediction of this theory is that they will go with each other and they will agree on this, 0.55 and 0.45. So we predict that A gets X plus half of the surplus and B gets Y plus half of the surplus. That's the prediction of this theory. And if you simplify this, you get this numbers. A gets X plus 1 minus Y over 2, and B gets Y plus 1 minus X over 2. So this is the same number, huh? Simplified. Okay? The surplus is 1 minus X minus Y. This red box is called the Nash bargaining solution. So Mr. John Nash was also involved in this theory. Okay? So if I have an outside option, and B has an outside option, and the options are not that great, the sum is less than 1, then the theory predicts they will agree with each other to this. They will agree to split the surplus. So this is the local view. So for each edge, you basically look at the outside option. What happens when I go outside? And then you make a prediction. Okay? So that's the first step. That's the first step of our theory. It's the most complicated step. Okay? So this might seem complicated, but it's actually not. If you think about it, it's what happens when A and B have outside options. Okay? So that's the first step to our general theory. Now we have two more steps, which I won't go about today. The ultimatum game and the notion of stable outcomes. This is the example of the triangle, when one of them can always steal. So the stealing is a problem, okay? So we have this notion that's part of our theory as well. And that leads us to the theory of balanced outcomes. And this one is the best theory that people know about how to predict negotiation. Okay? Okay, so let me stop here today so you get some idea of what we're talking about. Again, it's a very clever kind of thing about human negotiation. Question?
In a few words, what happens with the project?
You will get, so we'll finish here for the course. Let me make an announcement on the project. So there was we tried to make a very interesting and innovative, ambitious project on studying Facebook manipulation, but it basically didn't really work, and the main reason is that Facebook is actually much smarter than we thought. Facebook was actually banning these new accounts for some people, and we never know, maybe it would ban more accounts. There was no certainty that you could do this kind of extra account. That's the first thing. The other thing was that people were concerned that the Facebook conditions was not letting them create so-called fake accounts. But this concern is actually not a real strong concern, because these were not truly fake accounts. These were accounts created in the context of a scientific experiment. So this kind of experiment is normally allowed, okay? Even though Facebook basically says nothing is allowed. You can never investigate us, okay? If you follow it strictly, Facebook is saying, we know everything about you, but you cannot look at us, study us. This is not a tenable situation. So in terms of experiment, it is allowed, and actually the students would not be responsible for these accounts. It's the university who would be responsible, and essentially it's me and the university who would be responsible. Okay, so there was no real legal problem in these accounts, but the real problem is technical, that Facebook is actually very paranoid, and the measurement phase would take 4 weeks. And during these 4 weeks, if Facebook can be suspicious, they can always cancel people's accounts. So people might be waiting for 3 weeks, and Facebook would immediately cancel their account after. So this introduces unpredictability, and that means the project was not really feasible. People would be waiting, would be very stressed. Every day, Facebook could cancel their account. So that makes it not feasible, in fact, the project. So we decided that this wouldn't really work. We tried to do something clever and original. So me and the Jeremy Cooper-Blum, master student, and Lucille Dirks. But we see that it's actually much more complicated than we imagined. That Facebook is much more paranoid and defensive than we imagined. So this project is not possible, actually. So we decided we're going to cancel it. We are still early on it, and we are going to give you a more traditional project. So you're going to get a more traditional project where you'll get some data, real-world data that has been collected otherwise, and we'll ask you to do some kind of analysis on this. So it'll be more closer to projects from previous years. So it's kind of too bad, but we didn't really, so we tried to do something original and innovative, and let you really investigate Facebook, but it turns out it's not possible. Facebook is much more paranoid than we imagine, and it's like attacking a fortress. It's not one soldier who's going to attack the Barad-dûr fortress. Even strong one soldier, so one master student and one little professor, which is me, cannot attack a huge fortress. This is what we discovered, okay? So unfortunately, we had to cancel this project. Too bad. I think it's actually would have been a very interesting experiment. It would have been a real experiment, okay, on investigating how Facebook's recommendation algorithm really works and how manipulative they are. But it seems Facebook does not let itself be examined so easily. In order to examine Facebook, you have to make a much more thorough attempt, and you have to have a much bigger team. Okay? So basically, one master student is not very easy to study Facebook. So there you have the story. But the fake accounts was not really something to worry about, because Facebook conditions are extremely paranoid. They basically forbid anyone to do any kind of investigation. But this is not legal, in fact. So if we were to do this, it would be perfectly okay. And any kind of a protest, it would have actually been between the university and Facebook. And probably Facebook does not want that publicity, okay? So they probably would have just let it drop. So it was not really a problem, this notion of, because it's not really a fake account where you're trying to get some kind of a gain. It's a fake account purely for scientific examination. So this is not a very serious problem. So that was not the problem. The problem was really the paranoia, and that makes the project impossible, unfortunately. So that kind of answers, right?
Yeah, it does.
So, in fact, I can make another announcement. So actually, we learned quite a bit from this on how Facebook reacts. And this will all be explained in Jeremy Cooper-Blum's master's project. So if you want to learn about Facebook and about what really is going on here, you should read Jeremy's master's thesis. So this will be done in June. So he was finishing in June. So I think this will be very interesting, okay? If you want to learn about Facebook and how they are, basically, Facebook is a very dangerous company. They have a lot of power, and it's extremely hard or impossible to understand how they work internally. And so Jeremy has some very interesting insights. So I recommend you all to read his master's thesis when it appears. Okay, so that's all.